In this video, we begin our talk about various design patterns. A design pattern is a widely reusable solution to commonly known design challenges in software programming projects. Typically, it involves a few classes with clearly defined roles and the recipe how to use these classes to solve a specific problem. Our handout for this set of topics is design patterns. And this handout has a number of samples using C++ programming language. In our presentation, I would like to stay entirely neutral and use only UML and perhaps occasional Java examples. But feel free to look at these C++ samples in this handout if you're interested in C++ coding solutions to these design patterns. So these are the categories of design patterns that I would like us to try in our course. A set of creational, structural, and behavioral design patterns. In many projects, creation of objects like the challenges related to which part of the system creates which objects, what object is created first, which one is created next, what data is needed to construct all objects is quite a challenge. And this challenge requires making many important design decisions at early stages of our user requirements analysis and system design. A UML class diagram does not tell us anything about the sequence of object creation. That's why UML class diagrams kind of fall into the category of a static view of the system design, right? So we typically use this object diagram and class diagram as part of the static view of the system. A sequence diagram is an important tool to visualize and validate object creation. So UML sequence diagram belongs to the dynamic view of the system. As we study design patterns, we will use both class and sequence diagram quite extensively. So object supply creation sometimes involves hundreds and even thousands of different types of objects. It's definitely a challenge, and some object may be constructed from other objects in case of a composition and aggregation. Some objects require configuration definition in order to properly construct all internal parts. Some objects are almost effectively constructed from copies of previously built prototypes. So variety of object creation, therefore, becomes a significant component of the software besides just using already existing objects. Their creation may be a challenge. So creational design patterns hide low-level details of creation algorithms from the client. And of course, when I say client, it's the rest of the system who is using parts of our design pattern. So oftentimes, these design patterns return class interface and not reference to a concrete class. Let's take a look at the factory design pattern. In our design pattern coverage, we often use the term client, client software, which is, like I said, is part of the system which is using components of our design pattern. For example, with factory design pattern, client software wants to create objects without specifying subclass types. It really means that the client says, I want an insect object capable of flying, or I want an insect object capable of jumping. Okay, so we don't say generally, let's create an object of type grasshopper. It is precisely the factory responsibility to decide exactly what is the type of the class to create the requested insect class. So it may be an ant or bee or grasshopper. So here in this example, we need a variety of payment types in the system. And in this example, we make cash payment, credit payment, credit card payment, payment by check, part of the payment. So there's a base class or superclass, and these are our concrete subclasses. So therefore, if we need to be able to create payment objects in the system, because of the inheritance relationship between superclass and subclasses, Abstract Factory is an interface-based solution intended to create an object supply which is made up of related objects from the same family of a hierarchy, namely the subclasses in that hierarchy. So to illustrate, basically there's a part of the system which is a client, and this client part of the system wants to use these different types of payments. So the Abstract Factory design pattern will be accomplishing the task of creating these objects, but returning this level, interface level, reference to the client. So the client will have this reference at the same time when the objects of these types are created. Why is this possible? That is because we create this type of payment and this type of payment and this type of payment. So these are actual objects that we create. So I'm just intentionally trying to draw different dimension 3D boxes because internally they may be implemented differently. So I draw 3 different kinds of boxes, and yet they all inherit from the payment. So the payment component will be present in each one of these boxes. So there will be an identical part right here, like this, and like this, which will represent the payment object. And this is natural for the inheritance in programming languages. This is how class inheritance works. When you have this class inheriting from this class, at the time when this object is created, like this example right here, the payment will be made part of it. And likewise, all other types of payments will include internally the payment type. And therefore, it's not a problem for the system to basically store 3 references of these 3 different objects in the same container somewhere, where the reference is really pointing to the common part, which is the payment part here, and which is also obviously the base class component of these objects. So you see, there's definitely the presence of payment in all 3 different types of objects. So therefore, it's quite possible for the rest of the system to create these types, but then at the client level, use only references to the base or superclass part of each of these objects participating in this hierarchy.